This is the BrainChip podcast. Hear from our thought leaders about neuromorphic computing, beneficial AI, and how BrainChip's Akida is pushing AI to the edge. This podcast is a place for investors, practitioners, and anyone interested in the future of AI.
Hi, this is Steve Brightfield from BrainChip. We're here for our recurring podcast, and we have a unique guest. It is my pleasure to speak with Miguel López, head of robotics at Arquimea Research Center in Tenerife in Spain. This is a vast enterprise that is composed of a large research organization and a commercial enterprise. And Miguel, to start, maybe you could briefly introduce Arquimea and its core mission, particularly within the context of the research group's innovation and technological solutions.
Hello, Steve. Well, thanks for having me. It's my pleasure to be here talking to you. Arquimea is basically a Spanish company. It's like 20 years old, sorry. And our R&D activities are mainly focused on developing technology to help society to move forward and to progress. And we're also focused on building a sustainable solution with this technology. So our Arquimea Research Center is, as you said, located in Tenerife. And we do fundamental research on several topics, including artificial intelligence and robotics, which is the team that I lead. So yeah, basically our goal is to develop new technologies to solve society challenges and provide value, reaching the market with those technologies.
That's fantastic. Well, BrainChip, we've been really happy to be working with you in a partnership to further your research. Maybe you could tell us what initially attracted Arquimea to BrainChip's Akida technology and neuromorphic computing, leading to this engagement and partnership.
Yeah, of course. Just for a little bit of context, for the last 4 years, we have been researching two topics within the robotics field. We understand these two topics, like robotic embodiment and perception/cognition, as limiting factors on the agility and efficiency of robotics in general. So on the perception side of things, one of the things we understood is that whenever you try to reach information from the environment, you start piling up on data, and then you need increasingly more computing power. So one of the first things we learned was that by using a completely different paradigm, like let's say changing from a classical computing and perception to a neuromorphic computing and perception, we should be able to increase the efficiency, lower the amount of data required, and at the same time having some benefits out of how the neuromorphic networks and perception and computing works. So the reason why we approach BrainChip is because we found it to be an easy-to-use, readily available neuromorphic computing platform with the right tools for us to implement what our expertise is, which is basically algorithms and neural networks on the platform. For us, it's really important to be able to tackle this fully neuromorphic perception from three different perspectives, which are the sensing, the neuromorphic sensors, the algorithms, which is what we do, and the neural networks, spiking neural networks, and the computing, neuromorphic computing solution, which is basically BrainChip. That's the platform that we chose to be able to integrate on our platform.
Fantastic. So you basically understand well the data overload when you have streaming data coming in, and you either have to buffer it and store it, or you have to process it immediately, and that can consume a lot of power. Once you selected the BrainChip as a kind of a target technology for this, maybe you could describe the nature of how you work with BrainChip and what kind of objectives that you aim to achieve with us. Yeah.
So the way we use BrainChip is basically we used it as the main chip to compute spiking neural networks. In our research, what we had to do is to build a neuromorphic data set of pictures, high resolution pictures, and we train several spiking neural networks to do several different tasks, but mainly about detection and classification tasks. Okay, so very typical tasks in the AI field. So what BrainChip does is basically it's all these nets are trained to be computed on BrainChip, and we do it with all the tools available to implement different architectures in the chip. So when we say we use BrainChip, we basically are saying that all the system that we are implementing is fully neuromorphic, and all the spiking neural networks are fully running on BrainChip on the silicon device. That's how we use it. We obviously couple it with a JSON ordering to be able to handle all tasks of the embedded system, because it's a real world application. But the nets are fully working on the BrainChip device, on Akida one.
Okay, and this was on the demonstration solution we saw for enhancing water safety, right? You had an AI-powered detection solution utilizing BrainChip's Akida in combination with the PROPHESEE event-based cameras on drones. What were you trying to solve with this? What challenges were you trying to solve with this kind of combination of technologies?
Well, the main challenge was to be able to deploy a fully neuromorphic system on a real-world application. When we started researching on neuromorphic technology, we found out that not many complex tasks had been demonstrated in the field. So that was the first challenge that we saw as, okay, we can do this. So we aimed at selecting, again, neuromorphic sensor, and a neuromorphic computing platform, in this case, PROPHESEE and BrainChip. That was the architectural solution that we found. And we had to develop this image data set. We had to do a data set of fully neuromorphic pictures and label them, which is also a challenge. We had to find out how to implement this workflow for a fully neuromorphic system. That is, it's very, very easy to do on classical devices, but it's not so straightforward on fully neuromorphic systems. And as a functional goal, the idea was to be able to detect people on a coastal area and then classify them depending on their behavior, whether you're basically walking on the beach or entering the water or just floating, swimming, surfing, or you're in distress. Those are kind of the categories that the system can classify people within. The reason we chose that application is fundamentally because it's a big problem. In Spain, nearly 400 people die every year of drowning. It's a lot of people. And it's also a very dynamic scenario. So everything is moving. The drone is moving, the waves are moving, and optically speaking, is very challenging. You have glares, you have high reflections, you have fog, mist, you have transparencies. So it's a very, very challenging application. So we really wanted to put a fully neuromorphic system to the test. It was a combination of goals, as you can see.
Yeah, so this wasn't just a research implementation. It was something you felt could actually be commercially deployed, and you solved the real world deployment kind of challenges. What were all those unique challenges solved with this data sets and training that you put together, or was there some algorithm adjustments that you made to make this work properly?
I think the combination of some algorithms that we implemented and our own data set, fully neuromorphic data set, it's actually the reason why we managed to solve it. But if I had to score it, I would say that the creation of a dedicated data set for this application was basically the main reason why we managed to solve it. It took us a lot of effort, to be honest, and we had to implement a way or develop a way to actually label the neuromorphic images. It's not straightforward as you could basically do it with a classical imaging system. Yeah.
You said that, frame-based approach to this, it was pretty straightforward, right? A traditional frame-based computer vision is well known, and how to collect the the data sets and train them. But you went ahead and selected something more difficult, this event-based computing solution. So what advantages did it offer you to take that extra effort to go to a neuromorphic or an event-based complete system? Here now you have both the event-based sensor and the event-based computing coupled together. You can't look at these images and easily label them like you would with a frame-based. So what advantages does this provide to you when you did the deployment?
I think the main advantage that we found, it was at the system level. So when you consider the whole system, you start seeing efficiency and latency and metrics that only exist at the application and system level. So at that level, we identify neuromorphic perception and computing as a very promising technology for future developments. Obviously, the classical architecture for perception and computing is more advanced, basically because it has been developed for years and years now. But we see a lot of potential in a change of paradigm in the perception and computing architecture. So even if we found great efficiency on how BrainChip computes these spiking neural networks, but even if we didn't, we still see a lot of potential for future developments, and that's good enough to keep researching. On the other side of things, when you do new things, you also find the holes in technology. So we found a lot of holes when doing the data set, fully neuromorphic data set and labels and all that stuff. So that, from the research point of view, that's also very interesting because it helps us understand what can be improved in the workflow and what can we do to make it more streamlined and approach or approximate to the efficiency acquired over the years for the frame solutions. So in general, I would say it was a very good result, all in all, for this research and development project.
Mm-hmm. So have you demonstrated this water safety solution on the drone with potential customers, or is it really been focused as a research project? And how do you anticipate the solution potentially being deployed?
We have, from the beginning, it was supposed to be just a research project, okay, where we could extract direct comparison from in between frame solutions and fully neuromorphic solutions. That was the let's say, scientific objective. But since we managed to demonstrate the capability of doing it fully neuromorphic, we have managed to demonstrate this solution to several customers nationally and also internationally. And we have managed to secure some grants because of these results to develop new projects, new research and development projects. And we are discussing also with national institutions and organizations to create wider demos to demonstrate this technology on different locations, different weather, different, the same application, different locations, different coastal regions. So in a way, expanding the data set and expanding the solution. So yeah, the result has been very, very interesting in that regard.
Do you anticipate other use cases for this outside of water safety then?
It's interesting that you asked that because we have been considering several other applications for very similar architectures, but different use cases. At some point, I believe we're going to start mixing both our research line in robotics, which are robotic embodiment and perception, and these kind of fully neuromorphic perception systems are going to be integrated at some point on our own robotic platform. So that's, for one, it's one of our future applications for sure. But even in defense and security, we have found several other applications like maritime security, like underwater surveillance, that kind of stuff. That it's on a very niche market, but that can be benefited from a neuromorphic approach. So yeah, definitely.
So this could be considered really kind of a foundational research you did, that it has a lot of different applications, and you're already exploring that. I know that you had the robotics lab there, and applying it to robotics, that is an enormous kind of potential there with the interest in robotics. You had developed this technology on our Akida 1 chips, which is somewhat older technology, and we recently introduced our Akida 2 technology, which offers larger models and deeper precision and so forth, but we didn't have a chip to provide to you. So what we did was we put the design on an FPGA in the cloud, and we offer that to customers, and you were one of our first beta testers of that technology. What did you learn from that beta test, and what does that show to you for the promise of Akida 2 versus Akida 1?
Yeah, we're very glad to be one of those first beta testers. It's really interesting because most of the time, whenever you work on an embedded technology, you don't work on the actual device. I mean, you're not connected to the drone itself. So for us, having the cloud available, it's like having the actual chip on the desk, and that's actually great. With the benefit of being in constant communication with you guys, developing the actual chip, to get support from you and optimize the implementation of SNNs with your tools, and also give us somehow any insight or any feedback that we can give you to maybe improve the tools, or even modify some things, some feature versions of the integrated circuit. So so far the team is really happy with the architecture and the way of working with Akida Cloud, to be honest. Yeah.
Well, that's really great to hear, because that was our goal, and I think you encapsulated it by saying, putting a chip on your desk. That was the intent, and I'm glad to hear that worked. How do you see this impacting your future research? Do you see this as something that would be incorporated in that, or is this something really just for model development?
I think it's very versatile, because even if you have a distributed team, some of this is the small stuff that you never predict, right? Whenever we collaborate with several institutions across the world, so whenever we had some piece of technology, some hardware, we need to start working on logistics to deliver this piece of equipment there. So basically, having an access to a cloud that it's actually computing in the same way as you would do with a device on the desk, it makes our lives easier when you have some people working remote, for instance. So I think if anything, it's actually accelerating our development process. So yeah, I really like this approach.
Excellent. Good. So maybe we should back up a little bit for the audience and kind of look at, from your perspective, what do you see are the significant trends to observe in edge AI and neuromorphic computing? You're kind of really in the forefront of applying these technologies to new applications, and you probably have a good viewpoint of where you see this technology going. And do you have any kind of feelings about that?
I do. I'm not sure how valuable they are, of course. This is just my opinion. And obviously, edge AI, it's a huge thing. We are basically working on a niche, on a corner of what edge AI is. What it's clear to me is that everyone is trying to bring AI to the edge, and everyone is trying to do it with as much power and as much capability as possible. That usually means lots of data and lots of computer power at the edge, as
Right.
that's not always available. So that's basically the reason why we entered into research in neuromorphic computing and perception and cognition, because we kind of understood, or that was our opinion back then, that at some point you will always try to use as much power as you have, right? And so even if the processor gets more powerful, you're going to try to do more stuff. So our goal was basically to try to get ahead of a different paradigm and change the way that information is decoded from the environment and sent to the processor and all the algorithms within. We are also considering not only doing perception as a computer vision, but also integrating several perception sensors on this neuromorphic architecture. That means that several types of sensors would try to be acquiring data from the environment from a multidisciplinary environment, or I don't know how to say it, but multimodal.
Sensor.
Yeah, exactly.
Multimodal.
Multimodal. You can think about touch. You can think about acceleration. You can think about the image as well, also vision. So I'm merging all of that on a computing platform, but as trains of pulses, not as matrices and numbers. It's a completely different story. Obviously, we're not probably the only ones doing that, but I think there's going to be a lot of challenges, of course, but in the end, I think a lot of benefits in terms of efficiency and agility. At the end, if I think of a robot, agility in the end, it's required. We cannot wait for a robot to be doing path planning for 2 minutes and then moving another 2 minutes and then stopping again and deciding where to grasp the mark for another 30 seconds. And then, no, you need real agility. And that comes from the robotic embodiment limitations and also the perception and the cognitive limitations as well. So in a way, we're trying to solve those limitations at the same time with the two lines, the two research lines that we are chasing. So yeah, to summarize it, I think there's a lot of potential on the neuromorphic perception and cognition in the next coming years. Yeah, and I guess and I hope BrainChip has a lot to say on that potential improvements.
We certainly do. We see the same opportunity that you do. I just, sense that you feel a lot more confident about this technology after this initial water safety program here, and that you're more committed as an organization to combining neuromorphic computing with other forms of computing to solve system level problems. What milestone do you have in mind for Arquimea using neuromorphics to further your research? It sounds like the ultimate goal is the more challenging environment of a highly dynamic, agile kind of robot solution. That might be the end goal. Is there some milestones between here and there that you see that you're looking to do within Arquimea?
Yeah, I think we have several milestones. Maybe not fully defined on the calendar, but
Yeah.
I can foresee a milestone where we can actually combine different type of sensors and compute them on a fully neuromorphic system and achieve a similar performance compared to classical. That could be, from my point of view, the first thing to do. And then from there, move forward to improve the performance. I mean, that's normally the way we work. We try to benchmark the current technology and then surpass it with a new paradigm. That would be the way that we would approach it. So the first milestone would be basically to integrate that system and to achieve the same performance achieved with the classical system. And then from that point onwards, I believe the most important thing would be to actually demonstrate that we can significantly increase the agility and the efficiency of a system with these characteristics. I'm thinking about a mobile robot with, again, multimodal sensing solutions, integrated, potentially even developing our own small sensors for some physical parameters. And yeah, basically the next milestone would be to demonstrate that we can actually achieve a fully neuromorphic perception and cognition system, so we can improve agility and efficiency as evaluation metrics.
Miguel, that's fascinating. And in having a system level approach like you do for the application of neuromorphics really shines a whole different viewpoint on what's possible in the future. And I think you're shaping the future with the work you're doing there. And it's really exciting. Having an expert like you to take our technology and apply it in a way that really demonstrates that there is a different computing paradigm than the classical computing paradigm to do a lot of these functions. And actually, these changes are almost necessary to achieve kind of the objectives that you're reaching is appreciated. So is there anything else you'd like to share about Arquimeia's vision for AI innovation or any other capabilities your organization you want to feature? I'm sure some of our listeners are going to be quite interested about Arquimea.
Well, in general, we are a very very courageous company. So I would say that we put a lot of effort in researching and developing disruptive technology. So most of the stuff we do sometimes is considered to be science fiction. And we are also very proud of this approach. So the idea of having a space where you can think about future technologies with an open mind, without an immediate market need, or not need. We also look for market needs, but without the pressure of reaching the market in 1 year, let's say, or 1.5 years. We look ahead at 5 years, 10 years time, and that's why we can take the time and the funding as well to reevaluate the computing paradigm and the perception and cognition on something as complex as a humanoid, for instance. Other than that, I would like to say thank you and thanks to BrainChip, because this collaboration, it's actually helping us a lot to establish this new paradigm. I personally believe that a fully neuromorphic system requires on tackling the whole challenge from a holistic point of view, and we need to work together with sensor suppliers and computing platform suppliers and or developers, and also develop algorithms that are optimized for the sensors, for the computing platform. At the end, it's kind of a triangle, and the only way forward is basically collaborating from a holistic point of view. That's how I see this collaboration and how important it is for us.
Well, at BrainChip, we've been really excited to work with your company and yourself and your team. The enthusiasm you guys bring to it and the insight on how to apply our technology is incredible for us. And I'm sure that we'll touch base with you in the new year and see how your work is going. And maybe we have some more innovations and developments that we can disclose there. So thanks again, Miguel, and your whole team. We appreciate your insights here. So thank you so much.
Thank you so much to you, Steve. Thanks a lot.
Thanks for listening to the BrainChip podcast. Please remember to rate and review on your favorite podcast platform.